What's up, AP Calc students? It's Mr. Ford here with another homework tutorial. Today we're talking about 5.2.4, and we're going to be doing all of the problems here except for 597b. We'll not be dealing with that giant piecewise function. We got a lot of work to do, so let's get into it. 593 is going to give us a function, f of x, x to the third, x to the 2/3, and we are going to find the minimum, maximum points of inflection for that. So let's get into it. When it comes to minimums and maximums, we're going to look at the derivative and figure out when it's equal to 0. I'm going to do that work over here because there might be a good amount of it to do. So we're going to take our time and map out everything before we start. Let's start with our derivative. F prime of x is equal to 3x squared plus, I got to think about this one. This is 2/3 times x to the negative 1/3 power. And I do want to clean that up. That's going to be 3x squared plus 2 over 3 times the cube root of x, like that. Now what we're concerned with is when this equals 0. When does 0 equal this whole thing? 3x squared plus 2 over 3 times the third root of x. With the sum involved, a lot of times this can be a little trickier than it might normally appear. But x is actually not too bad. I'm just going to move one of those terms over. I'm going to put negative 2 over 3 times the cube root of x over here equals 3x squared. Then I think it's a good idea to multiply both sides by 3 times the cube root of x. Or maybe it might be better to think about it as 3 times x to the negative 1/3 power, because then we can just add together the exponents there and there. We'll get negative 2 equals 9 times x to the negative, 5/3 power. And again, the question is when this is going to equal 0. Man, I don't know if it will. Let's think for a minute here. If I divide the 9 over, well, the nice thing is because it's an odd numbered root, it'll only be one solution, which is cool. Oh, these don't cancel out. Negative 2 over 9. I'm just going to leave that as negative 2 over 9. I might go to the calculator in a minute here for this one. X to the 5/3 power. So, wow. Man, at this point, I could raise both sides to the 3/5 power, and that would cancel it out. Yeah. Wow, this seems excessive for a problem like this. Hey calculator, what is negative 2/9 to the 3/5 power? This is ridiculous. To the fraction 3/5 power. That's what I'm getting for the only 0 I can see on this problem. At this point, I'm going to go over to my answer page and see if I got the same thing too. Let's see. I got to log in. So you can go ahead and skip ahead a minute while I got to do a couple things here. Should have set this up before I started, Ford. Come on. You're killing me. 8.4, that is not what I got. Okay. Well, did I make a mistake somewhere in the derivative then? 3x squared. X to the third plus x to the 2/3. 2/3 x to the 1/3. I suppose maybe a better strategy might be, I'm going to leave this here, this workshop. You know what might be a good idea is take our derivative, let's just graph it on the, and we'll see where it crosses the x-axis. 3x squared plus fraction 2/3 x raised to the negative 1/3. Like that. And we'll just do this on a nice standard axis, and we'll see. This is our derivative, so wherever this crosses the x-axis, that'll be a spot where we have a potential minimum or maximum. Bam. Oh. So it looks like there are a couple things I want to talk about on this graph. I wish I could zoom in a little closer on it. It's looking like, I'm just going to make it the full screen so you can see it. Looking like we have one spot where the graph crosses from positive to negative, which would create a relative maximum at that point right there. And we also have a point where it does not exist. Oh yeah, I guess I didn't see that before. If x is 0, the whole thing does not exist, so we got to think about that too. So I think I just made a math mistake somewhere in my notes here. I'm just going to get rid of all this extra stuff and use the graph from this. So I'm going to take calculator cam down a little bit, and then I'm going to show you what I'm writing down. based on this observation. So the first thing I want to know is what that point is where it crosses from negative or from positive to negative. So I'm going to use the 0 tool. Left bound, right bound, and in the middle is right there. It's looking like negative 0.5248. So my derivative was correct. I must have made a math mistake somewhere in that first part of it. I know that at x equals negative, let's see, I got to move it up just a little bit so I can see it. Negative 0.524. 525, I guess I'll round up. F prime changes from positive to negative. So there is a maximum. And I'm going to figure out the actual coordinates. Negative 0.525, comma. I'm just going to go back out to the original function was x to the third. So let's see, negative 0.525 to the third power plus x, negative 0.525 raised to the 2/3 power. That was the original function. I just want to know what the y coordinate is there. It's going to be 0.506. That's where there is a maximum. The other one is a lot easier to talk about. If you look back at the graph for a moment, there is a non-existent point. There's a spot where the derivative doesn't exist at 0. And that matches, because if you look at the actual function, if you were to plug 0 in for x right there, you would get an undefined derivative. And so there is also a critical value at x equals 0. Also, I know that's going to be a maximum because the graph changes from being a negative value to a positive value. So, sorry, that's a minimum because it's going to go from decreasing to increasing. It will happen kind of probably at a sharp corner, but we'll take a look at that in a minute. At x equals 0, f prime of x jumps from negative to positive. So there is a minimum at the point 0, 0. And that's an easy one to calculate because if you plug 0 into the original function, you just get 0 out too. Also, that takes care of our first derivative. Let's take a look at the second derivative for the point of inflection. F double prime of x, which is not going to be any more fun to deal with. It's going to be 6x plus, if we bring down the negative 1/3, it would be negative 2/9 x to the negative 4/3 power. And again, we're just going to rely on the graph to do this for us. We're going to do 6x plus in fraction form, negative 2/9, x raised to the negative 4/3 power. Just like that. I'm going to graph it right on top there. We're looking for any spot where this is equal to 0. That's it. And we don't really need to know. I guess we can find out the coordinates of it. But yeah, if that's 0, there we go. I see it happening right about there. Again, we'll just use the 0 function of our calculator. Make sure that I push the arrow down, so I'm talking about the red graph. Left bound over there, right bound over here, guess somewhere in the middle. It is about 0.244 or so. So at x equals 0.244, there is a point of inflection. Because f double prime of x changes sign. And the coordinates are going to be 0.244, comma. I'll go back out to the main screen. I'm actually just going to take my work from this problem and just change that to 0.244. Delete the negative, 0.244. 0.405, that's going to be the actual point. What's cool about this is at no point did we actually graph the original function. We could do that now, but we don't need to because we found all the information we had to. Okay, that took a little longer because I kind of made a mistake at the front. I should have done some research, but let's go ahead and fly through a bunch of others, really straightforward math problems. 594, we had to use all our derivative tools to differentiate all the expressions below. So let's go to town. Question A. Question A is a triple chain rule problem. I don't know if you guys see it or not looking at this problem right now, but there are 3 things going on here. There's the sign of x, there's the cube root of x, and finally x plus 3. There are 3 layers to this. If this was a chain rule, let's see, if this is a piece of candy, if this was a peanut M&M, it would be the peanut would be the x plus 3, the chocolate would be the square root of x, and the candy shell would be the sine of x. It's a triple layer. So if we do the chain rule, let's kind of work through it step by step. The first part is to have the derivative of the sine of x, which is the cosine. Let's write, it would be the cosine of the original inside. We're not going to touch it yet. Cosine of the cube root of x plus 3 times the derivative of the inside part. Cube root. So the cube root of x, the derivative there, that's x to the 1/3 power. So I have to think about this one. The derivative of the cube root of x plus 3 is going to be 1/3 times x plus 3, the original inside, raised to the negative 2/3 power. That takes care of the derivative of the middle part. And finally, we would multiply by the derivative of x plus 3, which fortunately for us is just 1. So we don't need to worry about that too much. It doesn't do anything for us. Now, there's a good amount of cleaning up we could do on this derivative. We don't really need to worry about too much. I am going to just write it as a fraction. I'm going to put the cosine of the cube root of x plus 3 on top of the fraction, because everything else is on the bottom. The 3 times x plus 3 to the negative 2/3 power. 3 times, well, let's just write it as the cube root of x plus 3 squared. That's your derivative right there. That's A. B is going to require our freshly, newly minted quotient rule. So let's review for a moment what's going on here. Our top function, f of x, is equal to 4 minus x squared. Our bottom function, g of x, is equal to x to the 3rd minus 2. So our f prime of x is going to be negative 2x, and our g prime of x is going to be 3x squared. Now, if you remember quotient rule, we start with the original bottom. It's g times f prime. You can find that if you're watching this video later after the fact. You can find the quotient rule printed for you in right here in the math notes box right above. We start with f prime times the original g, and we have to subtract the original f times g prime. You have to remember the what's going on here. When I was in school, I remembered that f was v and g was u, and I remembered that u go first. U go first. U times the derivative of v. Like this. I had a student one time who called this one high and this one ho. High up top, ho's down below, and he remembered that ho's come first. The original ho comes first. That's a fun one too. So whatever you want to do to remember that. So for our quotient rule here, we need our original g times f prime. We need x to the 3rd power minus 2 times negative 2x. I'm going to put that in front. Minus 3x squared times, in parentheses, 4 minus x squared. So there you go. Your original f, or original g times f prime, and original f times g prime. This all goes over g squared, x to the 3rd minus 2 squared. Walk away. Do not do anything else. Do not do any more simplification. You don't need to. You can't do it anyway. Who cares? That's the derivative. Let's talk about c next. C is just 1 over cosine of x. Let's think about this like a quotient rule. There are other ways to do this that we'll memorize later on down the road, but let's just think about like a quotient rule problem. I'm going to run out of room real fast in this space, so I might work off to the side for the future problems. We have 1 over cosine x. Let's say that f of x is equal to 1. That means that f prime of x is equal to 0. G of x is equal to cosine of x, and that means that g prime of x is equal to negative sine of x. So when it comes to the quotient rule, the original g times 0 is just going to be 0 minus 1 times negative sine of x. So it's negative sine of x. We'll change that to a plus in a moment. And on the bottom, we have cosine squared of x. So this ends up being sine of x over the cosine squared of x. Now, we could do a lot of trig identity stuff with this, but I'm going to circle it and leave it for later. I do want you to realize that this is equal to the derivative with respect to x of the secant of x, which we're going to learn the derivative for later on. We'll find a different way to write it too. So there's a formula for this. This is a preview question, question C. Let's look at question D. I'm going to start working off to the side on these ones because there's a lot of work to do for a lot of these. Question D is a product rule problem. Your first function is 6x minus 1. Your second function is the sine of 2x, which is going to require the chain rule. F prime of x is just simply 6. G prime of x is a chain rule problem. It's not a very difficult chain rule problem, though. The derivative of sine is cosine of the original inside, and then now you have to multiply by the derivative of inside, which is 2. So we put it all together. Here's our answer. We're going to have, it doesn't really matter with product rule which order you go in. So we're going to have 6x minus 1 times 2 cosine 2x plus 6 sine 2x. Just like that. Looks complicated, kind of is. You can simplify it, but don't do it. It's not worth it. Question E. You had another quotient rule problem. This is going to be a long video. I kind of knew that going in. E. I'll probably have to break this up into 2 parts the more I think about it. Again, E is another quotient rule problem. F of x on top is the sine of 3x. That's going to require the chain rule. G of x on the bottom is 2x to the third power. F prime of x is equal to 3 times the cosine of 3x. I'm doing chain rule in my head now. That's how good you are at this too. The derivative of the sine is the cosine of the original inside times the derivative of the inside, which is 3, and I went ahead and put that in front right there. The derivative of g is relatively simple too. G prime of x is just 6x squared. Finally, we can run this through the quotient rule. This is a quotient. So again, original g times f prime. 2x to the third. Actually, let's multiply it all the way out. No, let's not. 2x to the third times 3 cosine 3x minus 6x squared times sine of 3x all over the original g squared. 2x to the third to the second power. You can simplify quite a bit. Don't do it. Don't do it. Very rarely do you actually need to simplify your quotient rule. So we don't typically preach it ever. And then question F is going to require, actually question F is insanely simple, guys. It does require that you see something though. You do need to see that the sine squared plus the cosine squared is equal to 1. So question F is simply asking you, hey, what is the derivative of the square root of 1? You could go through a lot of work doing that problem and not see that. You could do it by hand. But at the end of the day, you're going to get 1 for the answer. Actually, you're going to get 0 for the answer. There's that. Whew. That's a lot of work. This is kind of usually the way we teach calculus is you'll front load your class with all of this stuff. You learn your derivative rules back in September, October, and then you start doing a bunch of these drills. The problem there is I feel like students get defeated before they understand the basic concepts of everything. So now that we've got a good understanding of slope and area under the curve, how they connect, now we're going to start looking at some formulas and doing a lot of heavy algebra work. So we'll get a lot of practice for this. On our half day on Friday, I have a circuit training for you to review these rules. So it'll be pretty straightforward. Let's look at 595. We're going to go back to physics for a minute here. When Rajit hit his golf ball at the 18th hole, it went straight up in the air. If he hit it with an initial velocity of 144 feet per second, write an equation for the ball's velocity at time t. That's pretty simple to do. The velocity on Earth in, I guess we're looking at feet per second. The velocity here is going to be negative 32t. That's just a constant from Earth being in feet per second, and plus the original velocity, 144. Assume the gravitational constant. Again, if you didn't know the negative 32, you could take the antiderivative of negative 32 and get negative 32t. That's question A. Question B is what is the velocity of the ball at 0, or when is the velocity of the ball 0 feet per second, and describe the ball's position at that moment. This will tell us the maximum. This is for problem B. Negative 32t plus 144. If you do the algebra here, that time is going to be just 144 divided by 32, which in this case, according to my calculator, is equal to 4.5 seconds. That is how long it takes the ball to hit its maximum point. That is not the actual maximum point. That's how much time it takes to get there. Question C is going to ask us for the actual maximum. For the actual maximum, we're actually going to need to take the antiderivative of our velocity function, which is really easy to do, especially if you've been paying attention to these kind of problems. They always fall into the same pattern. It's going to be negative 16t squared plus 144t plus 0, because the initial height of the ball would have been 0 feet because it started on the ground. So all we got to do is go to the calculator and do negative 16, 4.5 squared, plus 144 times 4.5, and find out that our maximum height of 4.5 seconds is equal to 324 feet. And so at 44.5 seconds, the ball hit a maximum height of 324 feet. Bada boo, baba booey. 396, we got some integral problems. We just got lost in the weeds with some derivative questions, and now we got integrals. And honestly, this is calculus. If you ask people what they struggle with in this class, it usually comes down to this kind of stuff there. 396, hang on. My wife just sent me a text that is of great interest, so I'm going to keep going. 2 Petoskey High School band directors. Ooh, interesting. Oh. Oh, good. Good news from my friend. Okay, cool. Sorry for that. Question 596. Integral from 1 to 8 of the cube root of 27u du. That's going to be a kind of a tricky thing to think about. Actually, it won't be too bad. I noticed right away that the numbers 1 and 8 are perfect cubes. That's probably going to help us down the line. I'm going to rewrite this as 27u to the 1/3 power, because we're going to run this times du. We're going to run this through the antiderivative, anti-power formula. It'll look like this. Well, it won't be so straightforward. We'll think about it a little bit. We know we at least need something. We need 27u to be raised to the 4/3 power, because that will, when we take the derivative, we'll have the 1/3, we'll still have the 27u intact to the 1/3 power. We need our 4/3 to cancel out, so we're going to need 3/4 down here. However, if we were to take the derivative of this red expression now, the 4/3 would come down, cancel out with the 3/4, and we'd be left with 27u. But according to the chain rule, we would still need to multiply by 27. So we're going to need a times 1 over 27 out here in front to cancel that out also. So all said and done, what we're looking for is 3 times 27u to the 4/3 power all over 4 times 27, which is kind of a beast of a problem. That's going to be, oops, my syntax, 4 times 27 is 108. We are going to need that there. So, yeah, that's not so fun. We are going to evaluate this now from 8 to 1. Now that looks like it's going to be a bit of a beast, but it's not going to be so bad. 3 times 27 times 8 to the 4/3 power over 108 minus 3 times 27 times 1 to the 4/3 power over 108. We're going to let the calculator handle most of this work anyway, since we're probably allowed to. I would certainly want to. 27 times 8 raised to the 4/3 power times 3 divided by 108. I'm getting 36 for this first chunk. Same calculations. 27 to the 4/3 power is 81 times 3 divided by 108 is 2 and 2.25. So I'm getting, for the final answer, 36 minus 2.25, I'm getting 33.75, or 33 3/4. I like that answer quite a bit. We probably could have done this by hand, but who cares? I didn't. Is 3 divided by 108, is that a nice thing? 136. I guess we could simplify things a little bit over 36, but, well, who cares? Okay, next question. Oh, we weren't allowed to use a calculator? Whatever. Boo, 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 boo. Tomato, tomato, tomato. Hate that problem. Hate it. Let's do question B, which is very simple. Question B makes me laugh. Look at this. If you're thinking about this and paying attention, this is just a number. If you evaluate that integral from 4 to 18 of 6x minus 3, you're just going to get a number for the answer, and then they want you to take the derivative of that number. This is 0. Very simple. And then let me just check my answer really quick. I want to make sure I'm being correct about this without... Yeah. And then here, question C. Interesting. This is an antiderivative of the second derivative of f of x. And basically, the antiderivative cancels out one of those derivatives. The answer here is f prime of x plus c. So you take the antiderivative of the second derivative, you go up one level, you're back to the regular derivative, and that's where you land. Pretty cool, pretty cool. Yeah. Okay. Let's move on to question A on 597. 597 is actually pretty straightforward. What we're going to do is we're going to graph this piecewise defined function and determine if it's continuous and differentiable over all intervals. So let's try it. First of all, let's sketch a graph of it. This is just question A. We're not going to worry about question B, which can get a little hairy, not fun at all. What's nice about this is that the break in the piecewise function happens at 0. So we really got to think about just positive and negative values. 2x to the third power is just kind of like a cubic function that's been stretched down by a factor of 2. So it's just going to kind of look like this. I'm not going to graph it with any sort of accuracy, but it does level off towards 0 there as it gets to 0. And then 3x squared is just a parabola with, again, stretched by a factor of 3, but it's going to look kind of like that. That's your sketch, at least. As far as continuous, I can definitely tell you they're continuous. I'll show it to you right now. For continuity, what you want to do is you want to plug 0 into both of these functions and see if you get the same answer. Again, is 2 times 0 to the third power the same thing as 3 times 0 to the second power? And they're both 0. So, yes. For differentiable, you want to do the same game, but with the derivatives of the function. So f prime of x, I'm just going to write this right here in this space. F prime of x, the derivatives would be 6x squared for the first part and 6x for the second part. This is when x is less than 0. This is when x is greater than or equal to 0. So, again, if we plug in 0 to both these functions, the same thing happens. 6 times 0 squared does equal 6 times 0, and so 0 equals 0, and so it's also differentiable on all. I'm just going to leave that at there. So, yes, it's differentiable and continuous on all fronts for all values of x. Pretty cool. Don't like B. Moving on. 598s are actually really simple. Using the graph of f prime, determine the values where x has a local minimum, local maximum, or point of inflection. And we're going to justify our answer for all three. So we're going to write a little bit, but it's not too terrible. The first point of interest is -3. I would say f of x has a it goes from negative to positive. So it's going to decrease and increasing. So it's a minimum at x equals -3. And the reason why I know that is because f prime of x goes from negative to positive at that point. Again, there's a good amount of writing that goes along with this, but you have to demonstrate to your exam reader that you understand what the derivative tells you. We're going to say the exact same thing, but opposite for x equals 1. F of x has a maximum at x equals 1, again, because the derivative, f prime of x, goes from positive to negative. At that point. And finally, the point of inflection, which is going to happen right up here. That's going to happen at x equals -1. There's a point of inflection, f of x has a point of inflection at x equals -1 because f prime of x, here's an interesting way to write this, changes from increasing to decreasing. Now what that means is, another way to say the same thing is that because f prime of x goes from increasing to decreasing, this means that f double prime of x changes sign at that point. So you could think about the concavity, or you could think about the first derivative. Since the first derivative goes from increasing to decreasing, the second derivative will have a sign change because the second derivative has the same relationship to the first derivative as the first derivative has to the original function. So there's my 3 facts I know about that. And finally, a really base skill you must have, just being able to pick out what the original function was, what point we're talking about here, what's the derivative, and what's the derivative of that particular value. So these questions actually go pretty quick once you know how to read them. The key idea in the first one is that 1 plus delta x, that's what we used to call 1 plus h, that's the x. So the original function is 5 minus 3x, which means the derivative is just -3, like that. let's see, as far as what point they plugged in, well, you could think about, you need it to be 2. So we're talking about the derivative at x equals 1. So c is equal to 1. And f prime of c is -3 because it's always -3. It's a linear function. Very similar. If you look at that, the rest of these problems fall into line the same way. Here, the original function is, again, x to the 3rd power, whose derivative is 3x squared. The function, or the number they're plugging in, is actually just that number. We could have seen that in the previous problem right there. It's actually just the number -2. And so f prime of -2 is 3 times -2 squared, which is 3 times 4, which is 12. Right there. This last one is a little different. This is the alternate version of the what's the word I'm looking for? Formal definition of a derivative. It's slightly different. Limit as x approaches c of f of x minus f of c over x minus c. This gives you all the information right here in the problem. Actually, you can see it right away. F of x, well, that's just what that is. 2 times x to the 1/2 power. C is also given to us. It's 9. It's whatever this number is. So there's that. F prime of x, well, this is one you've seen before. This is 2 over 2 roots of x. And the 2 over 2 cancel out. It's 1 over the square root of x. And so I guess f prime of c would be 1 over 3. There you go. Well, got a little hairy there at the front. I could have done a little more research and maybe started the video off a little better. But the second question here is really the beast. We'll probably end up taking a look at some of these during class too. This is where we're really going to practice our new abilities. And you'll get a lot of practice the next couple days with these derivative formulas. But with product rule and chain rule and quotient rule as your allies, you're ready to handle pretty much every derivative to come your way. There's only a handful more of things we got to talk about with derivative formulas, which is a cool place to be at. So I'll see you guys in the next video. You guys are awesome. Keep it up.